All right, good afternoon, everyone. My name is Srijith Rajamohan, and until recently, I headed AI research at Redis, and today I wanted to talk a little bit about the agents that a diagnostic and remediation agent that we built for diagnosing issues with the Redis query engine. So we primarily built this as an agent to help our customer support agents with many of our customer queries. So Redis does provide a pretty rich suite of tools and pretty extensive documentation for these issues. What we really noticed is that at the end of the day, many of these complex queries get escalated all the way to the development team, which is obviously not conducive. So we built this to see if we can unblock many of them and reduce the time to solution for many of our customers. So what makes this challenging in particular is that unlike something like SQL, the parametric knowledge within an LLM is pretty limited, and we see that it gets it wrong quite often. So, and some of these queries are pretty context dependent anyway, where the agent must know what's actually missing from my query. So we had to build this spec-driven agent with skills and tools that goes through this clarify, diagnose, confirm loop in order to make this more reliable. So some of the things that we learned in doing this is that evaluating the final result is often pretty insufficient. How you get there or the trajectories matter quite a lot. And obviously, correctness is pretty important, but so is consistency. I like to say that the only thing worse than a system that doesn't work is something that just works occasionally. So this is something we really want to avoid. And lastly, inefficient trajectories are obviously expensive. One of the things that we learned the hard way is that these are also pretty error-prone downstream as well because of the length or context exhaustion as well. Obviously, using a more frontier model or more capable model will resolve some of these issues. What actually moved the needle for us was actually restructuring some of this knowledge and how agents access information. So essentially, we wanted to make sure that we provide sufficient information that it knows how to identify and access information and when to use it. So a couple of things that I actually want to call out here is these are some of the failure modes that we saw when we're building these agents, and I classify into 4 buckets roughly. The first, the correctness, completeness, and usefulness relates to the final results, and efficiency relates to the trajectory. Correctness is pretty obvious. Obviously, if your result is wrong, that's a problem. It can stem from a number of reasons, such as paths being wrong, it reads a metric incorrectly, and so on. So these are just hallucinations. Completeness, this is when it diagnoses only part of the issue and leaves the others unresolved, which is a pretty commonly occurring issue that we've seen. So usefulness actually falls into 2 buckets. The first one is when it actually gives you plenty of information, actually too much information, or very generic information to the point that it's really not actionable for the user. It is just overwhelmed with information. And the second one that was actually pretty interesting for us is when it provides information or advice that violates semantic intent. For example, telling a user who asks why my query is slow to reduce the number of search terms is technically correct, but it doesn't actually serve the purpose at all. The last one has to do with efficiency when the agent actually has repeated reads, backtracking, or does dead-end searches, thereby resulting in wasted tokens. But also, as I mentioned earlier, one of the things we noticed is that this also affected accuracy negatively as well. And most of these things can only be resolved by looking at the trajectory. They don't show up in the final result below. So we address this in 2 ways, or 2 dimensions. The first one was, can we actually take a look at the tool architecture, and what can we do there? So there are 2 things that we actually did here was primarily, can we split up the tools into 2 categories of setup tools and discretionary tools. So setup tools are always called at startup, as opposed to discretionary tools, as the name indicates, are called by the model based on the problem that you're solving. So a way to think about it is if you're starting on a new role, you might go through an onboarding process where they teach you what's happening there, who's doing what, who to talk to, and so on. So we can think of it that way, where the setup tools provide enough context for an agent so it knows how to proceed correctly and use the discretionary tools correctly, and it knows when to use it correctly. The second one was actually how we organize our knowledge base. Obviously, you can use the raw documents by themselves, but we saw better performance when we reorganized this into what we call a diagnostic playbook. This is nothing but a router plus a set of handbooks. And you can think of the router as, I've shown a small structure or snippet here, is you have symptoms, and you have a problem type associated with that symptom, and route to a handbook or a set of handbooks. So users don't come to you with saying, I have a certain symptom, they have concerns. It's the agent's job to actually map the concern to a symptom or a set of symptoms. Our job is to make it easy for the agent to do that, so that's what this serves. And in order to understand the effect of these interventions, we study these separately. So we learned in doing this, so we tested over a number of data sets, is we measured the end-to-end latency, but we also looked at the number of tool calls and the quality of the results. So the first one was a baseline setup, which was automatically generated set of tools. We noticed that it doesn't exactly perform as expected. It was slow, and the quality of results were actually pretty debatable. The last two I call minimal and full. They were actually generated by domain knowledge. They were informed by our domain knowledge of how Redis Query Engine works. So the difference between minimal and full is that full is a superset of all the tools you might find in minimal. So the way to think about it is if you have a tool such as get shard info, and you want to find out what the slowest shard is, you might have to call that and then perform some processing on top of it, as opposed to full, which might have get shard info and get slowest shard. So you just simply have to call it. Interestingly enough, that one did not perform any better. In fact, it was slower, and the quality was just marginally worse. So this sort of goes to show that tool overload is very much a real thing. And more importantly, what I'd call tool orthogonality or separability is pretty important. So at any point, if an agent is unable to determine if I should call B or C, it's problematic. So with setup tools, what we found out is that this is simply just minimal, except what we do is we moved a subset of those tools into the startup time. So what happens there is now it only has to make a selection between a smaller set of tools as it solves a problem. And here with setup tools and minimal, they perform pretty similarly till we took a closer look or drill down into the trajectories themselves. So what's interesting here is that with minimum, without setup tools, the trajectory is actually way more inconsistent. You have a lot more unique number of sequences. Obviously, not every unique sequence is an issue, but some of them can be problematic. The takeaway here is that reducing the number of variants, reducing the decision-making that an LLM has to make at any point reduces variance and also improves the consistency. And we were able to do this by providing setup tools which force an onboarding context. The second dimension was actually organizing information to Playbook. So how did that impact our results? So we organized this into two sets of buckets roughly, which is the answer quality and the trajectory quality. So answer grounding and specificity relates to the final results, whereas first pass success and dead end rates relate to the trajectory themselves. Across the board, we see improvement in performance when we're actually using playbooks as opposed to reading the raw guides. We also saw a 43% reduction in the total number of tokens and a 48% reduction in the total error rate. If you look at the last row there, what's interesting is that it also enforces instruction following a little better as well. The call out here is that reducing making it easier for it to actually access the information, not only reduce costs, but also reduce forgetfulness and thereby improved reliability. So obviously not everything is working as expected. There are things to be improved there. One of the things this is actually a prime candidate for are things like recursive self-improvement, which has been a pretty common theme at the summit here. So we'll probably have to look into something like that to improve performance even further. But we do see a reduction in many of the common failure modes. And lastly, to wrap up, if I can leave you guys with any takeaways here, there are two things I want to call out is measure the trajectory, not just the final answer, because many of the issues that we saw did not show up in the final result. We had to inspect the trajectories themselves. And if it is possible, structure the knowledge in a way that it's easy for an agent to identify and access, and take a look at your tooling to see what is mandatory baseline context versus what's discretionary or exploratory context. And the final thing I'll add is, if you can get to correctness, completeness, and usefulness of your result, and efficient trajectories, you're more likely to have production reliable agents. Thank you.